So, welcome to everybody. This talk concerns the topic 1 of the conference, and in particular seismic analysis of industrial facilities, perspectives and future developments of the new European Association of Earthwork Engineering Working Group. The goal of this presentation is to let you know the current activities and future development with this novel working group that deal with seismic design of non-nuclear industrial installations. The COVID-19 emergency is still critical, but the research activity need to go ahead, and I'm very glad to offer this talk for the scientific community. So this is a brief biography of mine. I got my PhD in 1999 in structural engineering with a postdoc experience in several universities, including the University of California, Berkeley. My research interests are mainly risk and resilience in seismic field of civil and industrial structures. I'm active in several committees for foreign associations like EASME or European Association of Earthwork Engineering, being chair in particular of a technical committee of EASME concerning seismic engineering, and of this new working group 13 of European Association of Earthwork Engineering that deal with the, as I told you before, seismic design of industrial installations. I'm also collaborating with several European and extra-European universities, and I'm author of more than 100 journals and conference papers. So all of us know the importance of industrial facilities and in particular of refineries for a modern society. In a world that has continuous need of petrochemicals, the role of these facilities is clearly of strategic importance. So let me introduce the main critical components of an hazardous plant. We have mainly storage tanks in which most of the oil and derivatives are stored. Then we have columns, typically used to separate oil in several components using chemical and physical reactions. We have also horizontal vessels in which the oil and derivatives are stored and modified. Then we have torches and flares as a part of the emergency operations. We have a lot of supported equipment, like one in the pictures, heat exchanger, but many others. And then we have finally hundreds of miles of pipes that transfer the oil and gas from end to different equipment. So this type of plants show in the past a very high vulnerability against NATEC events, accidents, the so-called technological events triggered by natural hazards. But even though the percentage of accidents caused by the earthquakes could appear limited, 80% in the pictures, that comes from a very well-known database, MIDAS. But the consequence in terms of economic losses, direct and indirect, and fatalities could be extremely high. For example, during the Cogelli earthquake, we had significant structural damages in several industrial installations. In the most famous one is Tupras refineries, in which we have damage in the plant itself and the associated tank farms with the crude and oil, in which multiple fires occurred. The majority of the floating roof tanks, 30 over 45 if I remember well, were damaged due to the exposure of the flammable material to the atmospheres, triggering tank fires that propagated the damage within the entire tank farm, destroying it. We had the evacuation order in a zone of 5 kilometers around the refinery, and the total damage was estimated to be around $315 million. That is particularly high. So according to the questionnaire survey by the Fire and Disaster Management Agency, facilities damaged by the 2011 Tohoku earthquake in Japan amount to more than 3,000. This is about 2% of the total surveyed hazardous materials facilities in the East Japan area. So they had 1,400 hazmat facility damaged by the strong motion, and about 2,000 hazmat facilities were damaged by the tsunami effects. And the fire occurred in the 42 facilities with oil leakage that occurred in more than 120 facilities, like in the pictures. This is the most famous accident occurred in the Chiba refinery during the earth. So these slides want to show the clear association of hazardous material installations with high seismic zones around Europe, demonstrating the emergency that need to be solved. We are speaking of Italy, Greece, Turkey, and so on. But what about Europe? The European regulations impose the control of measure hazard accident hazard, in industrial plants with the European 703 directive, the 18 of 2012, in which the risk analysis and prevention methods are required, also in the case of NATEC event, and the earthquake is explicitly mentioned. For these reasons, this group of volunteers joined in a working group with the aim to fill this gap, and this working group is called Seismic Assessment, Design and the Resilience of Industrial Facilities, and is the 13th group of European Association of Earthquake Engineering. So let me introduce the working group. It is composed by 11 partners, even though it is rapidly growing, and soon we will have a couple of additional partners. I'm the chairman, and I'm honored to have as a vice chair Professor Christoph Gutenberg, that I thank so much for the invitation to this conference. As you can see, we have many universities across Europe that we will provide very important contribution. So this working group is limited to non-nuclear industrial facilities, as I told you before. However, let's say existing guidelines and concepts already successfully implemented in nuclear power plants could be considered. These are the main goals of the group. The group intends to offer the scientific and professional community a clear overview of the problems and the viable solutions and tools. We have many experts in different fields: seismology, earthquake engineering, resilience, NATEC risk. And this working group will be a good occasion to familiarize with this important topic and be in contact with the community that is working on industrial plants and consequences to seismic events. The main outcome of this working group is to provide a contribution for the development of seismic code, including seismic design and innovative production system of measuring industrial plants within the 703 directive. So what are the motivation for creating this working group? Okay, to better understand these, we need to identify the many key aspects in the risk assessment of measure industrial plants. So in this respect, let me introduce the risk integral that characterizes the well-known performance-based earthquake engineering approach. And we can easily recognize here the main fields of investigation. Natural hazards, seismic response, that often is of non-deterministic nature, damage analysis that is common for structural engineering, but also aspects more familiar to industrial engineering, like loss analysis, that actually is in between, is important. Then we have consequence analysis, domino effects, and identification of damage scenarios. Here the resilience aspect is missing, but I will mention it later on. So, as you can see, we have mainly two words that need to be communicated: structural world and industrial chemical world, that often are difficult to exchange experience in this field. I call these communication problem, because in this framework we can recognize really a communication problem. So we have technical communities with different backgrounds, practices, and perspectives, and the interaction between micro, meso, and macro scale needs to be captured at the component level and the system level. Typically, meso macro scale are for geologists and civil engineering, micro and meso scales are for structural engineering, and the meso macro scale are mostly for chemical engineers, but these have to be merged in some way. As I told you, at component level, in which methods, mainly methods for structural engineering, are required under seismic point of view, and the system levels in which methods for process plant safety analysis are required, including the community, of course. To better understand the main issues in the risk analysis of hazardous industrial plants, like petrochemical plants, let's consider a nuclear power plant. That is different. To better understand this difference, let's see these. As well known in this case, in case of nuclear power plant, the risk is mainly governed by main events, the core melt, and it is enough to use a fault tree to identify the main critical components that contribute to the generation of the accident and mitigate the risk in this way. But in case of NATEC events, the situation is really different. We have a multiplicity of accidents generated by earthquakes. For example, the red dots here that are equipment that are damaged during the earthquake. But these can in turn generate multiple chains of accidents, like the red arrows that can hit in terms of physical effects the yellow equipment, the secondary damage units, and so on, in a domino effect fashion or escalation effects. So in this respect, phasing up the problem using a multiple level approach appears rather suitable, but really difficult. So for each element, the effect of damage propagation can be determined by using specific event trees, or for each source and target units, along with models for determination of physical effects, thermal radiation over pressure, that are more related to the chemical worlds, industrial worlds, to derive the related consequences. In all the slides, I suggested some readings that can help you to follow and to understand better details on this page. For this reason, the working group decided to activate several research trusts that are listed in these the next two slides, As you can see, we have seismic hazard, seismic design procedure for special structure component, considering also the dynamic interaction between primary and secondary elements like pipe, vessels, pumps, tanks. We need to improve the seismic codes and standards related to industrial facilities, and also working within the performance-based design concept for industrial facilities. Then we have vulnerability analysis and with the development of fragility curves and probabilistic risk assessment of components, often multi-components, elevated tanks or pipes and so on. We have also the idea to propose innovative passive-active seismic protections for facilities and installations, including new or novel proposals like meta foundations, for example. But we have also the idea to use the structure of monitoring a smart sensor to mitigate the risk. And in doing this, for the evaluation of risk and resilience, we have also in mind to apply artificial intelligence techniques like machine learning, surrogate model, and so on. So in these next 9 slides, I will be briefly describe some of these topics and the main related issues that you can find also in terms of details in these recorded references here for each slide. Concerning the hazard, the seismic hazard, for example, one of the main problems is to relate performances to the earthquake occurrence probability. As you know, this is a strategic in a performance-based earthquake engineering approach. It is possible in this respect to mutuate the limit states recognized in a nuclear power plant industry, like operating basis earthquake and safe shutdown earthquake, like indicated in the pictures. However, how to calculate the probability of occurrence that should include both structural performance and consequences? This is the question. The recent introduction of consequences classes in a new version of Eurocode 8 in the Eurocodes is a positive beginning, but we need more effort in this respect. The performance-based approach that is nowadays well recognized and used in civil engineering, in industrial engineering, is rarely adopted, still being the allowable stress design approach the most used one. One of the difficulties is to identify the damage conditions and quantify the related limit states. In addition, the typical critical fittings, pipe flanges, elbows, and so on, are usually over-designed, and the need to rethink the design procedure appear in some way necessary. This is another good example where the limit states of a bolted flange joints have been identified, including the yielding, the leakage, very important on consequence assessment. But works like these are very limited in the literature, so more effort appears necessary. Another strategic topic concerns the response of secondary elements like pipes and tanks, for example, is of a paramount importance. And there are very few contributions on this. For example, a recent shaking table test at the Eurocenter laboratory in Pavia has been performed on a component system. Is pipe frame plus pipe plus tank, and many interesting aspects emerged, including the identification of limit states, flow response spectral identifications, and so on. And we are still working on these, but we receive positive feedbacks from the scientific community, and we are encouraged to go ahead, of course. This has been developed within the SERA project, the Seismological and Earthquake Engineering Research Infrastructure Alliance for Europe, in which many other important research projects have been developed. The fragility analysis of industrial equipment is another topic that has been highly investigated in the literature, especially for storage tanks, as you know. But many other equipment need to be analyzed. Moreover, an investigation on the fragility curves in terms of loss of container appears necessary for consequence analysis. But as before, very few contributions were found in the literatures, and more effort is needed. Another good example of fragility analysis of storage tanks has been recently investigated, in which the effect of floating roof has been included. In this respect, more effort is needed, given that the past earthquakes demonstrated the dangerous effects that excessive sloshing of a floating roof can cause to storage tanks. See, for example, we can mention, for example, the Kogeli earthquakes, in which, as I shown you before, most of the damage was caused by the excessive sloshing of the floating roof. All the previous aspects would be joined in the risk analysis that need to include also consequences analysis within loss of containment and the related physical effects, and then cascading or escalation effects, as they are called in the literatures. And there are few contributions in this direction. One of these is shown in the pictures. You can have more detail in this publication, in which a framework based on Monte Carlo simulation has been proposed and implemented in the software, in a specific software, Priamos software in particular. But many aspects need to be clarified. For example, what risk measures would be used? Economic losses, fatalities, or what? There are questions that are waiting, these are questions that are waiting, of course, and answers, and this working group want to work in this direction. Finally, resilience is a very young but attractive topic. Pioneer work on this subject has been proposed by Roma Tre University concerning the resilience of the plant itself. This is the framework that we proposed, in which we use some resilience metrics, and we identified the recovery functions using a specific analysis of recovery models. We propose in particular specific recovery models. Some details can be found in these publications. However, the extension to the resilient community appears of paramount importance, and there are no contributions on this subject, or at least we have not found it yet. Of course, the interest of industry and the insurance on resilience are, in my opinion, well recognized and are surely waiting an answer. And but this topic need to be well developed in the future, because very few contribution has been proposed, as I told you before. In this respect, for example, what are the right resilience metrics? Economic losses, direct, indirect economic losses, fatalities within the plant, in the community. Okay, these and many other answers need to be provided, and long-lasting research activity on this subject appears in the horizon. This is my opinion, the opinion of the working group that I chair. So, as a last slide, I would like to show the main goals of the working group 13, in which all partners are working and giving, but this is to give a message for the community that there are strong interest in developing developing these topics, encouraging it to work hard along this line. Basically, we want to prepare preliminary guidelines for seismic assessment of industrial facilities as a foundation of the design code at the European level. We want to spread knowledge through workshops, seminars, and tutorials in collaboration with other associations like ASMI, Pressure Vessel and Piping Division, for example, or Japanese Association of Earthquake Engineering, or Pacific Earthquake Engineering Research Center. Some of these collaboration has already started. We want to promote public events for the discussion of these previously shown aspects. And we want to organize also special sessions in a key conference, especially in European, at the European level, but also in the world-wide level. Sedif conference is a very important conference in this respect, and I would like very much the organizer for this occasion. And finally, we want to promote projects within European research programs in the field of infrastructure risk and resilience. So this is the end of my presentation, and I would like to very much for your attention.